except their fuselage life has been extended 40 years. So they will actually outlast the B-2. Okay.
Yep.
Yes, Larry?
Earlier you talked about frequency surge. What can you still get through on? That sounds like an expanded cell scan.
It is. And with a software-defined radio, what you do is you have, because you're going to know all the frequencies ahead of time, if there's X, have X number of virtual receive channels going in your software-defined radio, digitize the band. You're not trying to transmit. Just digitize the whole band, have all these channels, 27 channels available, and just be correlating on all of those channels for the message to come in. And the transmitter, because remember, in a modern HF system, we're going to have a CSAC, tell me what CSAC is. It's a chip scale atomic clock, a chip scale atomic clock. So the nuke goes off, we're in synchronization with each other. Time slots, TDMA. This is my slot, this is your slot, this is my slot. Nothing's changed. We have intimate knowledge of what the communication was just before then. I even know where you are. So my slot comes up, I try this frequency, I try this one, this one, this one, this one, this one. I keep doing this. You know that I'll be doing this. This is a protocol I go into. When we lose a link, I start doing this. When the nuclear event detector goes off, I start doing this. And then when it's possible for you to receive me, you will. And you will the first time. Because the SDR is staring at all these frequencies at the same time. So this is the bleeding edge of what we're working at with the Air Force to try to persuade them to fund an ARC 190 upgrade, because you have national strategic interests. I had asked at Offutt if we should classify these high-level ideas that we're talking about. And they said, well, actually, no. Because, he said, there's two sides. If China, if we want to pick on China for right now, if China wants to blow up our satellites or do an attack, if they knew that we had a 190 that would keep the 135 tankers in the air, they would probably not pull the trigger. So he said it's probably in America's interest to advertise the fact that we can do this and have this capability than to keep it black secret, carved and hidden away from the public, because they would think, well, we just do that and all the airplanes are going to splash. Yeah, see, so it's a deterrence. It's a deterrence. Which is why I'm telling you this thing today. Okay, anything else on the nukes? All right, let's talk about antennas now. Total different subject. A vertical, biconic type thing, vertical polarized. Here's a horizontal one. We're going to talk about what's happened in the past. Now, before I go into this, I want to talk about something. From 1932 until the mid-1970s, RCA and the Navy maintained triple diversity receivers for running teletype. And they ran these through the war, World War II, Korean War, Vietnam, everything. They ran HF vacuum tube radios up until the mid-70s. They were triple racks, and they weighed 2,000 pounds. And those, yes. In fact, Art Collins made triple diversity receivers and dual diversity receivers.
Nuclear hard.
Yes, right. So they are heavy. They are the epitome of boat anchor. But something happened in the mid-70s that changed all that. We modernized a lot of radios. The tube radios went away. But what happened is we didn't take the idea of having 3 antennas or 2 or 4, just more than one, the paradigm of more than one. We didn't transfer that idea into the next generation, the transistorized HF radios, because of what? Satellites. Satellites. Satellites came in and everybody accepted satellites into their heart deeply. And they just said, they minimized HF and said, just do sideband, and that's it. That's all we need. We don't need to upgrade it. We don't need 3 channels. We'll just have one. If we need it, it's a backup just for satellites. So that's what they did. Now, the point is, for 50 years, they ran HF between Riverhead, New York, and Europe, RCA did. They had 41 channels, 41 receivers, and each receiver was triple diversity. Had 3 antennas, each one 1,000 feet apart. And they ran 45.5 baud radio teletype for 50 years without errors. They delivered bank drafts, millions of dollars, transactions, all the communications from one country to another, diplomatic stuff, was all run over radio teletype for 50 years with digital modes, albeit big vacuum tube modems and 45.5 baud FSK. It was just 2 frequencies. And they did it without errors. And the way they did it, they didn't have digital error correction, they didn't have interleaving, they didn't have forward error correction. What they had was they had smartness. They prevented the problem. And we're not taking advantage of this today. All right, here's an ionogram. This is what you would get if you did the thing at Johnston Land, send a pulse up in the air as a function. Here's frequencies, and here is it coming back from different altitudes. Like 4 megahertz bounced back at 240, this is kilometers, isn't it? Yeah, kilometers. Came down. So this red one, what happens is when you transmit a planar wave, a horizontally polarized wave, up into an ionosphere that has no magnetic field. Imagine that, no magnetic field. It would go up, it would bend, it would bend and come down like a prism, right? It would go up planar and it would come down as a prism. Now, when you add the magnetic field, it changes the recipe. It behaves differently. HF is never bidirectional, all right? So if the best path between Barry and myself is this frequency, the return path will never be that frequency unless he and I are aligned along the magnetic equator, all right? Which we never are, right? So the best frequency will be a different frequency. Receive will never match the transmit path. It won't, it can't. So what happens, what comes down when I send a planar wave up is it splits. The ionosphere is bifringent. That means it's magnetic. And depending on the direction you're going, it bends at a different point. So it goes up, and what happens is it turns and it comes down. Half of the power comes down as right circular polarization. It comes down as right circular polarization in the northern hemisphere. And the other half comes down as left circular polarization, and they're not coming down at the same location, right? So you get these 2 things coming down. They overlap a great deal. And you'll have, well, I'll tell you what, in the length of this table, you will have 4 copies of the signal coming down, rotating right hand, and it'll hit like this. It will. There'll be 8 of them. There'll be 8 of them in about a meter, all right? So it's huge. It's like this color band. You don't have a signal coming down. You have a whole bunch. So your bits are smeared. Your data, your voice is smeared and spread spatially over this. Now, when you have these two waves coming down, or just plain multipath, the left-hand one refracts. See, the red one refracts at a higher frequency than this one does at this frequency, right? So at a higher distance. So it's a higher distance, so it's going to go up further before it starts coming down. It's going to land further away from you. So that's why these 2 things are not the same. Now, it's the direction. This is called the ordinary wave, the O wave, and the green was the extraordinary wave, which is the left-hand circular polarized one. And they use an X for that. So X and O waves is what's happening. That's what you see there. Now, what they do is they take this data, and this is the electron density. They take this data, and you'd say, well, after 10 meg, it goes out into deep space. That's true when you're beaming straight up. But normally we have an angle, right? And they turn this stuff into really cool information down here. And this is frequency as a function of, meaning it's a sky wave. It's a low angle radiation, a low angle bounce. And so we're going way up to 30 megahertz. That's really crummy. But altitude and frequency that works. So this is what the nuke guys did not do. They looked at this and said, oh, good. I mean, there's no communication beyond that because nothing came back. Well, that's not true. There's never communication beyond this critical point here. Not straight up. It just punches through. But at an angle, it refracts off. Okay, let's go on. here is, I already told you this. You can see that they're coming down at different locations. So we'll keep moving over that. That's what HF looks like in terms of time. We've got hundreds of hours of this stuff, and you've got these huge suckouts that happen. So this is 1,000th of your power is arriving over here. It's just really a horrible thing. And that's normal. That's a good day. That's a good day. So how did they send teletype, radio teletype, for 50 years without losing characters? Through that. And this is the station they set up in 1930 to do it. That's Harold Beveridge of Beveridge Antenna fame on the right. Okay, here's a picture I took last year. We're almost done. East-west dipole set up for 10 megahertz to listen to WWV. And here's a north-south one, orthogonal to it, and a tree, and a mulberry tree. About 15 feet off the ground, horizontal. So this is a two-channel flex listening to these signals simultaneously, exactly the same frequency. You're listening to a guy speaking. So these are voice syllables. Blue is lack of energy. Green is some energy. Yellow is stronger, and red is much stronger, okay? So this is time going down, 5, 10, 15 seconds going down. So these are pauses in the syllabic nature of speaking. But look what we see. Look at this. This is a frequency selective fade where the signals are adding up to nothing. Look, so at this time right here, only that frequency is disappearing. It's nulling out at that frequency. This is okay, and this is okay. This one is not. Yeah, you can see a pattern. You know, a child could say, I see what it's doing. It's drifting up. And it doesn't always drift up like that. It's generally upward and to the this is a lower frequency to the left. Time's going down. So it's drifting like this, and it'll drift across the entire spectrum and fade away. It'll go over a couple megahertz and then fade. Then they won't be canceling anymore. So, but at the same instant, I took these at the same instant. Look what this is doing. All right? This one's got 3 hits of selective fading, and this may have a little contribution here, but maybe not. But the point is, if you sit and watch these, what you'll see is the fades will be in one channel, one polarity, and then it'll change to the other polarity. And 30 seconds later, it'll move back to this polarity. It'll move back and forth like this. So, yeah, you can hear it in your, yes, exactly. And so what they did for 50 years is they had hardware that just looked at the amplitude of the signal and didn't sum them. It switched between them in an intelligent fashion, looking at this in real time. So they had 3 antennas running, and they would switch between these. So that was a year ago. Last night, I fired up the rig, and I looked at, what was I looking here? This is the same frequency as the previous one, but now I don't have a 50-foot antenna. I've got 260 off-center fed dipoles, and they're up at 30 feet. So it's higher, it's bigger signals. And look at what's happening. We have frequency selective fading. This is 7:30. The previous chart was about 10 o'clock at night. So it's different now. It's different, but that's where the virtue is. They both have selective fading, but it's different selective fading. So the combination of these two add up to something that works much better than either one of them individually. Here is the same thing, a minute later? That's 33. So we've moved in time 5 minutes up or so. Oh, and I changed the antennas. I've gone to the vertical now. So we have an east-west antenna and the vertical. The vertical is really, really terrible. Lots of energy lost, faded out there compared to the off-center fed dipole. So here's another one with the, now I've gone down to, where am I at? I'm at 7.38 megahertz. So here's some digital stuff. This is in the ham bands. This is a broadcast station, and you can see the difference. Over here, there's not much difference. I don't know if they match, but they're being faded in a way. It's hard to tell there if it's beneficial or not. So that's 749 last night. Now let's go to the ham bands. This is what I found most interesting. This is most interesting. And the reason is, now, this picture here, this is just a few minutes later. This is 749. Oh, rats. It's 750 something. I didn't update my chart. But look where we're at. Here we're at 7.38, and I've moved down 300 kilohertz. So I've just moved down the band a little bit. The fading's still happening here. These signals are so narrow, you don't notice it. Look at that.
In other words, you're losing bits, but you don't know it.
You don't know. You can't see it. It's not obvious as a big, wide piece of spectrum with interference going through it. If you sit and study it long enough, you'll find out that the fading is present, but it's just not as obvious. So it's kind of an interesting thing. You got higher energy here, but good night, that thing's 260 feet long. So energy is not the way to compare a vertical to this, but the fading aspect. So I'm not sure what that takeaway is. It could be if you're doing just narrowband stuff. I know in some articles that are 50, 60 years old, they say that, the amateur community was running mostly CW back then, and so they didn't need diversity. They would say that. So they didn't need diversity, or they didn't benefit much from diversity. And I don't know if that's what we're seeing here, as it's a narrowband signal, quite narrow, so it doesn't affect you very much. I don't know. Your energy is concentrated here, and a fade would go across, but it would only be a short piece of time. Anyway, so I thought that would be a fun thing for you guys to see. I think that's all. Well, there's a couple things. This is what Rod Bloxham did about 8 years ago. This is real radios talking into a channel simulator. So they're not going over the air, but it's real radios, real modems, real transmitters. And if you take a given error rate, 1 part in a million, with 4 channels, 17 and a half or something, 17 something. Well, if you don't do anything, the difference is what, 12? 2 S units, so 12 dB. We're leaving on the table simply because we have 1 antenna to work with. So that gives you a rough idea what it looks like. And there's a number of scholarly articles that come out, and they have numbers ranging from 10, 12-ish to 20. So the answer probably lies somewhere in that range. Okay, I said that. All right, that's where we're at. I think that's the last slide. Yeah, questions on diversity? Al?
Tim, you just showed examples of 2 different antennas that you were comparing. How geographically separated were those antennas?
2 answers. When I'm running 2 east-west off-center dipoles, they are on top of each other. They're at the same tower, and they are orthogonal, right? 90 degrees apart. They're a foot apart vertically, so they don't touch. Now the vertical, when I bring the vertical back in, this is 150 feet south and west, south and yes, mostly south of where those 2 dipoles cross over on a different building, vertical, a big metal barn. So, yeah, so these pictures are data energy collected from exactly the same the feed points are within 12 inches of each other, but they're different polarizations. Yeah. Larry?
Where's the difference there? Spatial diversity and phase diversity. Spatial, where the antennas are separated.
Right.
Phase is where they're...
Right. So this is not spatial diversity. This is polarization diversity. I'm sorry. This one here, this one is polarization diversity. I'm doing north, south, and east to west. And I have connected these. One time, I did one experiment with Charlie where I got a 90-degree delay line, a piece of coax, right? And I summed them together so that the 2 antennas fed into one receiver as circular polarized data, right? And it actually worked. It did. I was surprised. It was visibly different, visibly better.
Circularly polarized from space.
Yes, it's coming down circularly polarized. And the cool thing is, if I have a right-hand circularly polarized antenna, right? The X wave, the X wave, it's rotating left hand. you'll have 30 dB of attenuation. That whole X wave goes away and doesn't bother you then. Yeah. It was quite impressive when I did it that one time. I've been meaning to get back to it, but it's been a year. Barry?
So would you characterize this as a high incidence angle or a low incidence angle? I mean, 9 megs from Florida.
It's probably low. It's 1,000 miles. But it's not like it's coming from Brazil or something. I think the answer is this. A person should have 3 antennas like this. And I'll tell you what I'm working on right now. I didn't bring pictures of it, but I took this antenna, this 260-foot antenna. I was using the east-west one, and I got a signal. I don't have a picture of it. I got a certain signal to noise, right? I'm looking at a signal, certain signal to noise. I then took a 7.5-inch ferrite rod that was a 1/2 inch in diameter, and I put 7 turns of wire on it and a low noise FET preamp with a gain of 1. Note 0 dB, right? And I ran that into the second channel. Now the difference between 260 foot of wire and 7.5-inch ferrite rod sitting on a wooden ladder was 12 dB. The signal to noise was only 12 dB different. So if you took 3 ferrite rods and assembled them as an east-west, a north-south, and a vertical one, right? And had 3 low noise amps right at that point, and you ran them down and combined them and got the 12 dB of diversity that Rod Bloxham showed on his test. Now you're talking about, I can run HF reception as equivalent to a 200-foot antenna. I could stick it in my attic, because most people have wooden roofs. And it would be a little ball about 12 inches in diameter. And you wouldn't have the fading problems. It would work like a big antenna, right? So the architecture would require 3 receivers. But anyway, so you can kind of see the things I'm doing. I could put that on a B-52. I could do things with that. I could get diversity on a B-52 or something small. And that's what I'm playing with. Yeah, Steve?
Does all of this research and stuff make your flex a professional tax deductible expense?
Well, I did have it in. It's been spending about 1/3 of its time in Collins, doing stuff like this. We're doing a lot of things with it. Mike Heineck took it and tried to make it meet the B2 specs, right? Tried to do the ARC 190 stuff with it for B2 program, and it just doesn't have the rejection. It just doesn't meet the intermodal requirement. So, we couldn't do it. Flex worked Flex was just standing right behind us, wanting to see that data because they've never done that kind of detailed analysis of their own radio. They're selling to, but yeah. So anyway, fun stuff. Anybody else? All right. Thank you.
That's all we have for today. Thanks for coming. Think of any other ideas here?
Yeah, both down there. I don't know who that's for.
We have a 6-meter amplifier that the club has had for years. It puts out
Oh yeah.
100 watts, right? He tested it. Anybody's interested in buying it, $200. Seems how most radios now put out 100 watts on 6 meters. So if you've got an older radio, you could use that. Yes.
Also, CVARC has announced that the 146.745 megahertz repeater will start using tone access approximately October 1st. The tone used will be 192.8 hertz. That's pretty much it.
All right. Yes.
Also through CVARC, there's a discussion of should there be a 450 DMR repeater.
Right.
And, I had gotten a...
Oh,
Yeah, run.
run!
Oh, it's starting to rain too. So I would like to introduce for discussion the possibility of tearing down the UHF D-Star.
Okay, wait a second. They discussed this last Thursday also. DMR. The club, CVARC, has already approved up to $3,000 expenditure for purchase and installation of a UHF D-Star using the 443.6 channel frequency setup.
D-Star or DMR?
Or DMR, sorry. DMR at 443.6, reusing the antenna, the feed line, the duplexers. So the 443.6 doesn't use very much.
True.